Welcome back to Basic Electronics. Last time we looked at a diode circuit with two diodes. In this lecture we will continue with that example and consider some specific cases. We will consider two other diode circuits and obtain the VO versus VI relationship for those circuits. We will also check our analytic results against circuit simulation results. Okay, so let us begin. Let us now look at some other configurations. First, let us remove this branch by making R2 equal to infinity. So now we have only this circuit, and to begin with, let us make Vs1 equal to 0. So now this is our circuit. This second branch is gone, and the VO versus VI relationship is as shown over here. It has only one breakpoint somewhere here, and let us now try to understand this VO versus VI relation. Let us first figure out where we expect this breakpoint to be. That breakpoint corresponds to the situation in which the diode just begins to conduct. That means we have about 0.7 volts here, and this current through the circuit is still very small, let's say 0. So we have 0.7 volts, 0 volts here, and no voltage drop across R or R1. So therefore V in is also 0.7 volts. So we expect the breakpoint to be at Pi equal to 0.7 volts, and that is what this shows over here. Okay, if Vi is less than 0.7, then the diode is off, and therefore no voltage drop here, and VO is then equal to Vi. That is this line here with a slope equal to 1 and passing through the origin. When the diode does conduct, that is when Vi is greater than 0.7 volts, you can work out the relationship between VO and VI following the method that we discussed earlier. The important thing is the slope of the VO versus VI line in that region, and that would be given by R1 divided by R plus R1. In this case, R and R1 are equal, so therefore the slope will turn out to be 1 by 2. So that is the slope here. Okay, let us continue with the animation, and notice how this Vi of t is being traced, and with the help of VO versus VI and this t versus t graphs, VO as a function of t gets constructed. The diode is off in this region, and that's why it appears in red. Okay, so that is the end of one cycle. What will happen if we change this 0 volts to 2 volts? In that case, for the diode to turn on, we require 2 volts plus 0.7, that is 2.7 volts as Vi. For Vi greater than 2.7, the diode would conduct, otherwise it would not conduct. So what we expect is that this breakpoint will shift to 2.7 volts, somewhere there. Will these slopes change? This slope of course does not depend on any resistance values. It simply represents VO equal to VI. What about this slope? This slope is given by R1 by R plus R1, and since we are not changing the resistance values, that slope would also remain the same. So let us see if that happens. And we observe that the breakpoint has indeed shifted to 2.7 volts, and the slopes have not changed. Next, let us look at the situation in which Vs1 stays at 2 volts but R1 is made very small, say 10 ohms. So this is 10 ohms now. What would happen now? The breakpoint would not change because we are not changing this voltage, but this slope will change. That slope is given by R1 divided by R plus R1. Now this R1 is changing from 1K to 10 ohms. So the new slope would be 10 ohms divided by 1000 plus 10, that is 1010 ohms. So it is 10 divided by 1010. That's a very small slope. So we expect that this line would appear almost as a horizontal line. So let us see whether that happens. There. Now notice that the output voltage has got clipped at this point, and that is why this circuit is called a clipper circuit. Let us do another experiment. Let us now keep this branch and remove this branch from the circuit. So let us make R1 equal to infinity and R2 equal to 1K to begin with. Vs1 does not matter anymore because this is an open circuit, and Vs2 could be 0 volts first. We can change it later. Now what do we expect to happen? So this branch is not there and Vs2 is 0, so therefore this is a short circuit. And now D2 will conduct if Vi is less than minus 0.7 volts. So therefore the breakpoint is given by Vi equal to minus 0.7 volts. When Vi is less than minus 0.7 volts, a current will flow like that, and you should derive the VO versus Vi relationship in that case and show that the slope would be given by R2 divided by R plus R2. When Vi is greater than minus 0.7 volts, D2 will not conduct, no current, and therefore this voltage drop is 0, and then VO would be equal to Vi. So let us check that out. Here is the VO versus Vi relationship. This is the breakpoint, and that is at Vi equal to minus 0.7 volts. In this region, Vi is less than minus 0.7 volts. The diode conducts, and the slope would be given by R2 by R plus R2. Since R2 and R are equal, this slope would be 1 by 2. In this region, D2 does not conduct, and therefore we have VO equal to Vi. What would happen if we change this Vs2 to 3 volts? Let us take this as the reference node for convenience. Then if D2 is conducting, then we have 3 volts minus 0.7 volts. So this node would be at 2.3 volts, and if D2 is just about to conduct, then these voltage drops are 0, and therefore Vi would be 2.3 volts. So that would be the breakpoint, and these slopes are not expected to change because we are not changing the resistance values. So let us check that out. Alright, so here is the breakpoint now. This slope is still 1 by 2, this slope is still 1, and the breakpoint has shifted to 2.3. What if we change this 3 volts to minus 2 volts? Then we would have, with respect to this reference node, minus 2 volts here, and minus 2 minus 0.7, that is minus 2.7 volts at this node. And Vi equal to minus 2.7 volts is then the breakpoint. So we expect the breakpoint to shift to minus 2.7 volts, and if we don't change these resistance values, we don't expect the slopes to change. So let us check that out. Alright, so here is our breakpoint, and that is indeed at minus 2.7 7 volts. Next, let us change this R2 from 1K to some very small value like 10 ohms, leaving this VS2 at minus 2 volts. In that case, we don't expect the breakpoint to change because that is determined by VS2 and this voltage drop across the diode. But this slope will change because that is given by R2 divided by R plus R2. Okay, let us check whether that happens. So we will make R2 equal to 0.01K, that is 10 ohms. Compute. And now we see that the breakpoint has not changed. It has remained at minus 2.7 volts, but this slope has become nearly 0. And as a result of that, notice that the output voltage has got clipped over here, and therefore this circuit is also a clipper. It clips in the negative direction. Here is our next diode circuit example. This is our input voltage Vi, that is the output voltage Vo, and we want to plot Vo as a function of Vi for Vi varying from minus 5 volts to plus 5 volts. And this is the ID-VD relationship for the diode that we will use, and it is of course the same as what we used previously. To begin with, let us consider this circuit with the diode D conducting, and in that case we can replace the diode with a battery 0.7 volts as shown over here. And now let us write KVL equation for this loop here. What do we get? We go from here to there, we come across a rise of Vi, so that comes as minus Vi. Then we have a drop of 0.7 volts, so that is plus 0.7 volts, and then we have a drop again, so that is plus Vo, and now we are back to the beginning. So these three must add up to 0, and that gives us Vo equal to Vi minus 0.7. So when the diode is on, that is the relationship between Vo and Vi that we would expect. We could of course get this by inspection. Let us take this node as the reference node, that is 0 volts. With respect to this reference node, this node is at Vi, this node is at Vo, and then we have Vo equal to Vi minus 0.7. So sometimes it's much easier to just get things by inspection rather than writing KVL, worrying about signs and so on. Alright, let us now look at the second case, that is the diode not conducting, and in that case we replace D with an open circuit as shown here. And in this case the output voltage is given simply by voltage division, that is R2 divided by R1 plus R2 times Vi, like that. So we know what happens in these two cases, that is when the diode is conducting and when it is not conducting. Let us now worry about the input side, and the question we want to address now is at what value of Vi will the diode turn on. Let us start with Vi equal to 0, and in this case obviously the diode cannot conduct because it does not have the 0.7 volts it requires, and therefore we are looking at this circuit here. Now imagine that we start increasing Vi. As a result, this current will increase and the voltage across R1 will start increasing. Now the voltage across the resistor R1 is nothing but the diode voltage Vd, and when this voltage reaches 0.7 volts, that is when the diode will start conducting. And what is this voltage when the diode is not conducting? That is given by voltage division. So Vd is R1 by R1 plus R2 times Vi, this equation here. As Vi increases, Vd increases, and for D to turn on we need Vd equal to 0.7 volts. So we put this equal to 0.7 volts, and that gives us the condition for Vi at which the diode will turn on, and that is given by this expression here. and when we substitute values for R1 and R2, we get Vi equal to 1.05 volts. So if Vi is 1.05 volts or greater, then the diode conducts, otherwise it does not conduct. Alright, we now have the complete picture. If Vi is greater than 1.05 volts, then the diode conducts and VO is given by Vi minus 0.7 volts. If Vi is less than 1.05 volts, the diode does not conduct and VO is given by this expression here. And now we can put all of these things together and plot VO as a function of Vi as shown over here. So this is the region Vi greater than 1.05 in which the diode is on, and in this region the diode is off. When the diode conducts, dVo dVi is simply 1, and that is what we observe over here. And when the diode does not conduct, the slope is R2 by R1 plus R2. R2 is 0.5 K, R1 is 1 K, so this is 0.5 K divided by 1.5 K, that is 1 by 3. So this slope is 1 by 3. One might wonder at this point whether the circuits we are looking at are practically relevant. Do they have any applications in practice? The answer to that question is maybe not directly, but in the process of looking at these circuits and analyzing them, we are definitely learning many useful techniques, and these techniques will surely be very useful when we look at some practical applications. So hold on, and very soon we will come across circuits which are practically relevant, interesting, useful, and so on. Here is our next example, taken from this book by Cedra and Smith. And there are several other interesting diode circuits given in this book, so therefore you should definitely look it up. Alright, let us look at this circuit now. This is the input voltage Vi with respect to ground, that is the output voltage. This node is sitting at 1 volt with respect to ground, which is not shown in this circuit, and this node is sitting at minus 2 volts. We have 3 diodes, D1, D2, D3, so the circuit definitely looks very complicated, and let us see how to go about analyzing it. Since we have 3 diodes here, there are 8 possible states for this circuit. This D1 can be on or off, D2 can be on or off, and D3 can be on or off. So therefore there are 2 raised to 3 or 8 possible states, and therefore the circuit analysis surely looks very complicated. But once we realize that it is much easier to find the status of each diode with respect to VO, then things are much simpler. And what do we mean by that? If VO is known, then this voltage difference is known, and therefore we can figure out whether D1 is conducting or not conducting. And similarly, this voltage difference is known, and then we can figure out whether D2 is on, D3 is on, or D2 is off, D3 is off, or just one of them is on. So if we start our analysis with respect to VO, then we find that it is much easier. Here is our VO axis. This is VO equal to 0, 1 volt, 2 volts, minus 1, minus 2, and so on. And to begin with, let us figure out for what value of VO or for what range of VO D1 is going to conduct. When D1 conducts, it can only allow current in that direction, and therefore this voltage drop across R1 with plus here and minus here would only be positive. And as we go from this node to this node, the total voltage drop would be 0.7 plus some positive voltage drop. Let us say that this diode D1 is just turning on. That means the current is just starting to build up, and let us say that the current is very small, so that this voltage drop across R1 is negligible. In that case, between this node and that node, we have only 0.7 volts, and if this is 1 volt, VO must be 1.7 volts. In other words, VO equal to 1.7 volts represents the boundary between D1 conducting and D1 not conducting. Any value of VO greater than 1.7 volts means that D1 would conduct. And this observation is marked in this figure like that. This is 1.7 volts. For VO greater than 1.7 volts, we can say that D1 is on. Let us now look at D2. When D2 just begins to conduct, this current is still small, and we don't have any voltage drop here, and then the total voltage drop between this node and that node is 0 plus 0.7, that is 0.7 volts. And that would happen if VO is 0.7 volts lower than minus 2. So that means VO must be minus 2.7 volts. And any value of VO lower than minus 2.7 volts would also mean that D2 conducts. So that is indicated over here. This is minus 2.7 volts, and for VO less than minus 2.7 volts, D2 conducts. Now as we increase VO in the negative direction like that, what happens is this current starts increasing, and therefore the voltage drop across R2 starts increasing, and at some point that would become 0.7 volts, and at that point D3 would start conducting. We will calculate that value of VO a little later. And the value of VO at which D3 turns on is indicated over here. So as VO is reduced, that means increased in the negative direction, first D2 turns on, and after some point D3 also turns on. So in this region we have both D2 and D3 conducting. Here we have only D2 conducting. In this region none of the diodes is conducting, and in this region only D1 is conducting. Let us now look at this region and find the relationship between VO and VI for that region. When D1 conducts, the current path is like that, and in this situation D2 and D3 do not conduct. There is no current in this branch, and therefore we have shown that in gray. Now as we have seen earlier, D1 starts conducting when VO becomes 1.7 volts. So VO is 1.7 volts when D1 just starts conducting, and this current is still small, so therefore this voltage drop is nearly 0, and in that case VI is equal to VO, that is 1.7 volts, like that. When VI is increased beyond 1.7 volts, this current starts increasing, and then let us see what VO is. VO is 1 volt plus 0.7 volts here plus this voltage drop, that means I times R1. And what is I? I is given by VI minus 1 volt minus 0.7 volts divided by R plus R1. So we get VO equal to 1.7 plus VI minus 1.7 divided by R plus R1 multiplied by R1. So that is the VO versus VI relationship in this region here. And what is the slope of this straight line? It is R1 divided by R plus R1, with R1 equal to 1K and R equal to 3K. This slope turns out to be 1/4. In summary, we have considered a few diode circuits and seen how they can be analyzed systematically. With this experience, you would be able to work out the VO versus VI relationship for other circuits of this kind. And it is a good idea to take up some diode circuit problems, say from a textbook, figure out its VO versus VI relationship, and then check your results with simulation. Okay, see you next time.